Hi everyone, welcome to another video of some math problem. Last time we've covered part A of this question and we found what the partial derivatives are and we also computed them. So for part B, we have another interesting question. It asks, is f differentiable at 0, 0? If yes, find df at 0, 0. If no, explain why not. So, a trick for thinking about this type of problem is to think about some simple examples of the directional derivatives and plug in some vectors values to see if they match with the derivative at that point. So if you have some ideas, feel free to pause this video and try it yourself. Okay, now I hope that you gave it a try and let's go through the solution. It is not differentiable. Why? Well, if it is differentiable at 0, 0, then our directional derivatives at that point should formally be equal to the derivative at that point, which is df of 0, 0 is equal to 2x. We got those values because we already found dx and dy from part A of this question. Okay, so dx is basically d1 and dy is basically d2. Okay, and I hope that you also found a counterexample in terms of directional derivative. So let v equals 1, 1, then dvf of 0, 0 is equal to the limit of f of that point plus tv minus f at that point over t as t goes to 0. Now, if you are now super familiar with directional derivative, here is a hint of how to think about it. So when you first see the form limit f a plus tv minus f of a over t as t goes to 0, it may seem daunting at first, but what this really is just a kind of modification of the partial derivative. So if you recall the previous limit definition of the partial derivative, we're basically taking a small change at that particular component. But in terms of directional derivative, what we are taking a small change is all the components. So it is kind of a weird name to call it directional derivative, since technically the partial derivatives also involve a direction. So if we have a small change in the x direction, then we're basically adding this little vector in the x direction. Or if we're taking the partial derivative in the y component, then we're adding this y component as a small change. But for directional derivative, we're adding a vector instead of one component. So a vector could be made up of multiple components. In this case, it is two components, so we're adding a small change or subtracting if you're thinking of the opposite direction. But in general, we're just making a small change in both the x component and the y component in this case. So when we add those up, we form a vector. So a way to think about directional derivative is to think about the limit of a small change in both components of the function as a vector. They add up as a vector, and that small change goes to 0. So you're basically replacing only one component in partial derivative to more than one component, all the components in directional derivative. So with that in mind, let's go ahead and compute this. So here we're taking the point at 0, 0, and we add a small change in components, which is t and t. Now, if I'm to do this step by step, tv is basically t times 1, 1. And since t is just a scalar, you could just multiply the t into the 1, 1. So you get t. Now, if you recall from part A, f of 0, 0 is basically 0. And now you have this equation here that is equal to dv. And because tt is now 0, 0, we use this expression, second one here, and just substitute x and y with t and t. Now we get 2t cubed plus t cubed over 2t squared over 2t squared, entire thing over t. Okay, so that is the f of tt, and this is the t. So if we simplify this, we get 3t cubed over 2t cubed, which just simplifies to 3 over 2. Now, 2/3 is definitely not equal to 2 times 1, right? Okay, so we write down the statement, but dv f of 0, 0 is equal to df 1, 1 of 0, 0. So here we're just substituting the vector 1, 1 into whatever the value here is. We have x is equal to 1, and there's no y, so we just don't care about y. So that is equal to 2 times 1, right? Which is equal to 2. That is not equal to 2/3. Thus, the conclusion is f is not differentiable at 0, 0. Okay, so the key point here is that you should remember that all directional derivatives at that point should also be equal to the derivative at that point when you substitute whatever the vector values are into this derivative. Okay, that's all for today's video, and I hope you guys enjoyed it and learned something new or reinforce your learning. Feel free to leave a comment below and ask any questions or just ask for some requests for future videos. I'll see you guys soon. Bye.